In this video, I want to cover the basics of probability. Probability is actually a vast subject. It's also a very difficult one for people to understand, probably because our minds actually are not trained to work that way. We're trained to observe the world as it happens, not what probability is talking about as it might happen. What other things are possible? The entire range of possibilities is not something that we are really programmed to appreciate. So there are a lot of pitfalls in probability and a lot of difficulty perceiving probabilities. I just want to focus on the basics of how probability works. And a probability basically describes any situation where there are a number of possible outcomes, and each outcome has some weight associated with it, which we'll call probability. The weight can't be below 0. The worst thing you could say is that it won't happen. It can't ever happen. That would be a probability of 0. If it's certain to happen, it has a probability of 1. But the probability will generally range between 0 and 1. And if you look at all the possible things that could happen and add up all the probabilities, they add up to the value 1. So that something is sure to happen, but exactly what it is what's uncertain. And probabilities, there are 3 basic strands. One strand is what's called subjective probability, where the probability is like a subjective assessment. What do you think the likelihood is? Candidate A will win the election versus candidate B. The second is from data, the relative frequency with which things happen. What is the probability of a 100-year flood? Based on historical evidence, how frequently does that happen? And the third strand is really derived from theoretical properties. Usually, the origins of probability come in gambling. And there are lots of gambling examples. And in fact, that's where I'll start. So if you think about, let's use a simple spreadsheet here. You toss a coin, and you toss it twice. The first time you could get a heads. I put heads twice. Oops. So if you get a head on the first one, you could get a heads on the second one, or you could get a tails on the second one. If you do a tails on the first one, you could get a heads on the second one, or a tails on the second one. So for 2 tosses of a coin, those are all the possibilities. And if you look at what you get either 2 heads, 2 tails, or a tails and a head. And actually, out of the 4 possible outcomes, 2 heads happens once. So the probability of 2 heads is 1/4. The probability of 2 tails is 1/4. And the probability of 1 heads and 1 tails is actually 1/2, because there are 2 different ways to get it. You can talk about that as a distribution, probability distribution over what happens with two tosses. The outcomes are 2 heads, 2 tails, 1 head, 1 tail. And the probabilities would be 0.25, 0.25, 0.50. Notice these are all the things that can happen. If you add up the probabilities, they add up to 1. Each of the outcomes has a probability between 0 and 1. So let's take a little more complicated example. Toss 2 dice. First one could be anywhere from a 1 to a 6, but since the second one has 6 possibilities, to account for all the possibilities, take a while to put it in, but it'll be a little faster now. All the possibilities are the second die for each row of the first. The second one has 6 possible values. Let me just copy that. So let's see what we get when we look at the total for the two. And with 36 possible outcomes here, you'll notice as you look at them, a number of the numbers repeat. So to talk about what the outcome could look like, the total for two, we have to know how many possibilities there are here. And you know from looking at and tossing dice that it could be anywhere from a 2 to a 12. But let's actually use a computer to look at that. If you install JMP with the Excel add-in, you can go to JMP here, make sure that it's set up to get the first row as column names, create a data table. Here's what we just created as the total. Notice that the outcomes range from 2 to 12. In fact, if you look at it, there is a mean here. This is actually a distribution. This is just like if you look at the distribution of any variable, well, we have a variable here. We have the total roll from 2 tosses of a die, and the total can, on average, you'll get 7. There's a standard deviation. There's a certain amount of spread out. It looks pretty symmetric. And we could talk about the probability of getting any particular value here. So for instance, how often do you get a 4? It's right there. There's 4. Notice it says 3 rows, 3 out of 36. So the probability should be 1/12 that you will get a 4. 1/12 of the outcomes here have 4s. Now, how could you calculate that the probability is in fact 1/12? One way of doing this is to think about what is the probability that you will get a total of 4. Each roll of the die, there's 6 possibilities. So any combination that you roll, any numbers, if you even cover up the numbers, there's going to be 1/6 probability of a certain number on the first die and 1/6 probability of a number on the second die. So 1/6 times 1/6 is 1/36 is the probability of any particular numbers to appear on the 2 dies. And then you have to say how many different ways are there to get a 4. And you can see how many ways you could get a 1 on the first and a 3 on the second, a 3 on the first and 1 on the second, or 2 on each. So there are 3 possible ways. If you multiply the number of possible ways, 3 times the 1/36, which is the probability of any particular set of numbers coming up, 3 times 1/36 is 1/12, which is 3 out of 12. You're going to see a better example of that in a moment here. Okay, let me close that one up for now. So let's think about a more complex example, at least a more complex one to calculate. Suppose you were flipping a coin 10 times and you want to know what can happen. Now, I could try to fill out the spreadsheet, but it's going to take quite a while to do that. I'm not going to do that. I'm going to do as much more basically. So think about what can happen with 10 flips of a coin. Each time you flip a coin, you could get a heads or a tails. So the probability that, let's say you want to know the probability you will get exactly 4 heads out of 10 tosses of a coin, assuming the coin is a fair coin, there's a 50% chance on each toss. So then the probability that you will get exactly 4 out of 10 heads, doesn't matter which 4 are heads, but 4 of them have to be heads, and each time that's a 50% probability. And 6 of them have to be tails, and each time that's a 50% probability. So the first part of this calculation would be one divided by 2 to the 10th power. Actually, let me do that a different way. Let's just do 2 to the 10th power. So what 2 to the 10th power represents is, if you think about putting the denominator of this probability, how many, every time you toss the coin, there's a half probability of getting either heads or tails. You're going to flip it 10 times. So there's 1 out of 1024 is any particular arrangement of heads and tails that can happen. Happens 1 out of 1024 times. Now the question is, how many different ways can you get 4 out of 10 heads? And that's pretty complex if you think about it. You could get the first 4 as heads, you get the first 3 as heads, and then the 7th would be a head. You get the first 2 as heads, and then the 4th and the 8th being heads. There's actually a lot of different ways. There is a formula for this. It comes from what's called combinatorial mathematics. And actually, Excel has a pretty easy way of doing this. It's a built-in formula. If you go to the math functions, it's known as combination. The number of combinations for a given number of items. What we have is 10 tosses, and we want 4 heads. Notice it says 210. There are 210 different ways that could happen. And so the probability is actually of getting 4 out of 10 is the 210 ways it can happen times the probability 1 over 1024, which is the probability of any particular series of heads and tails. Any one series that you observe, each one of them happens 1 out of 1024 times. Final probability is 0.205. This number is calculated with an Excel function here, but the way it's actually calculated is you use what's called factorials. You're looking at 10 times 9 times 8 times 7 times 6. If you have 10 tosses, that's 10 factorial. And you divide it by the number that you're looking for, which are called number of successes, 4 heads, 4 factorial. So this divided by 4 times 3 times 2 times 1 times n minus the number of successes, 10 minus 4, which would be 6 times 5 times 4. So the 6 times 5 times 4 times 3 times 2 times 1 would cancel. We would still have 4, 3, 2, 1 left. 4 times 2 would get rid of the 8. And instead of a 9, you'd have the 3 on the bottom. 3 would cancel into that times 3. There's the number of ways, 210. So that's what the shorthand, that's the longhand of what this shorthand function does. 210 different ways. But each particular way, 10 tosses happens as a 1 out of 1024 chance of happening. Using a little different software here, I can actually show you what this distribution looks like. This is known as a binomial distribution. For 10 tosses of a coin, where the probability is 50%, here's what can happen. You can get 0 out of 10 heads. Happens almost negligible probability. You can get 10 out of 10 heads, but that's almost never going to happen. The mean says it's 5, and that is the most likely outcome, but it has a little less than a 25% chance of happening. You're not likely to get exactly 5 out of 10 if you toss it 10 times. You can get a 4 and a 6 pretty commonly, and notice the 4, the probability is a little over 20%, which is in fact what we calculated here, 0.205. This is a distribution, just like any distribution you could look at of data. It's just that the data here is generated by a theoretical model that basically we know what the probability is of any particular outcome from the toss, from 10 tosses of a fair coin. Now, all of these distributions have a lot of math behind it. There's, in probability problems, is a challenge of what is the right probability function to look at. Is it a binomial? And that's the primary, I mean, that's an easy example, but in fact, we will often use other distributions, most commonly than what's called the normal distribution, but there are a whole bunch of other distributions running around statistical theory, more than any human being is capable of knowing. So which distribution do I use, and then how do I apply it? Those are fairly subtle and complex questions, but the binomial is a pretty straightforward one, and it applies anytime you have what's called n independent trials, where each trial, like a flip of a coin, has 2 possible outcomes with a constant probability of success. So success is considered one of the 2 outcomes. If it's a constant probability and they're independent trials, then the binomial distribution is a way of characterizing any number of successes out of some number. If you add, instead of 10, 100 tosses of a coin, now notice what happens. You're almost always going to be somewhere between, it looks like about 37 to 63 heads. That's the number of heads out of 100. 50 is the mean of this. It's the most likely outcome, but the probability of getting exactly 50 is somewhere less than 8%. Because if you toss the coin 100 times, I'm actually surprised it's as high as 8%. Getting 49 heads is pretty much the same thing as getting 50 heads. And you can see 49, 50, right in a range of 50, there's fairly similar probability of all of those outcomes. Okay, so rather than continuing with the sort of the gambling examples, let's see how this works when you're actually looking at data. And the data I'm going to use for this is actually a movie data set. So this has 5,043 movies. I think the excluded ones are the ones here that I didn't have data on the budget for, so I couldn't figure out profitability. But we got a bunch of information about these different movies. And to apply probability to this, I'm going to use the most common way of considering probability, which is the relative frequency. How often does something happen? So there are a couple of things here. 2 variables I'm going to focus on. There are a lot of different genres, types of movies, and there are a lot of different movie ratings. I've recoded these into sort of bigger categories because they're actually, historically, there have been a lot of different kind of movie ratings, and the genres are are broken down pretty finely here. If you put them in bigger categories, though, it looks something like this. G rating, mature rating, PG, PG-13, and an R rating. So out of, guys, I've excluded a bunch of movies here that don't have the budget data, but out of 3,504 movies with ratings, you can see 45% of them have an R rating. That is a probability. It's labeled a probability. Notice if you add up all the probabilities, they're all between 0 and 1 and for each of the categories, and they add up to a value of 1. In terms of the genre, and this is already recoded from what was in the basic data, but you can see comedy is the most common here at almost 29%. So if you pick the movie at random, assuming this is all the movies that have ever been created, it's really not, but it's a lot of them, at least the ones that ended up in the box office at some point in time. If you pick a movie at random, the probability it'll be a comedy would be 29%. The probability of it being a horror movie, well, that's a little less than 5%. Now, what I want to do is extend this to not just looking at the probability of what genre it is or the probability of what its rating is. What about the combinations of these two, the relationship between them? So let's look at how the two are related. How does the rating depend on the genre? And even though the picture can be described, let's look at this table, because the table actually is where you'll find these probabilities. So when you look at a table like this, you'll notice there's a total column. These are what's considered marginal probabilities. Looking at just one dimension of the data, this is telling you the marginal probability. This top one is missing, is we don't have a genre. Animation, 42 of them, there's 4 numbers in each of these cells. The top one is how many there were. The total percent is what percent of the total that is. And the column and row percents we'll get to in a minute. So this is in the second place, it's the total percent. 1.2% of the movies were animation. Jump down to comedy. 29.22% are comedies. If you look at the ratings, notice there's a total on the bottom, and the total on the bottom, R rating, 45.55%. Same thing we saw from just looking at the ratings alone. So these are what's known as marginal probabilities. They're in the margin of the table. There's something called a joint probability. A joint probability would say, what is the probability that it is a R-rated comedy? Well, find the cell that says R-rated and comedy. That's 463 movies out of a total of 3,504. 13.21% is the joint probability of 2 things happening, being a comedy and being R-rated. So if you pick a movie at random out of this data set, the probability that it is a R-rated comedy is 13.21%. The other 2 probabilities, the column and row probabilities, are what's known as conditional probabilities. Take the column probability. Conditional on it being in a column, what is the probability that it is a particular genre? So given that it is an R-rated movie, what is the probability it's a comedy? Well, that's a column percent. In the R column, of which there are a total of 1,596 R-rated movies, 463 of them are comedies, for a probability, a conditional probability of 29.01%. There's also a conditional probability of what the rating is given the genre type. That's the row percents. Given that you're on a certain row, what is the probability that you are in a particular column? Of the comedies, which are 1,024 comedies out of 3,504, what is the probability it's an R-rated movie? So given that it's a comedy, the probability it's an R-rated movie is this row percent, 45.21%. And one of the more subtle and confusing things in probability theory is the fact that these two conditional probabilities, which have the same words in them, are not the same thing. The probability of it being a comedy, given that it's R-rated, is not the same thing as the probability that it is R-rated, given that it's a comedy. The probability that it's a comedy, given that it's R-rated, is the 29.01%. The probability that it's R-rated, given that it's a comedy, is 45.21%. Not only are those different, but they're actually related. And there is something called Bayes' rule that actually talks about how they're related and can get you to compute one of these from the other. Okay, so the relationship between these two conditional probabilities is, you could actually write out a formula here. Let me see if I can get that on the screen pretty easily. Maybe I can do it here. So I want to know the probability that it is an R-rated movie, given that, that's the usual way of notating it, given is the vertical line, given that it is a comedy, can be written as the probability that it's a comedy, given that it's R-rated, times the probability that it's R-rated divided by the probability that it's a comedy. First, let's make sure that that's true here, that it works. The probability that it's R-rated, given that it's a comedy, that was the row probability, the 0.4521. It should be equal to the other conditional probability that it is a comedy, given that it's R-rated. That's the column probability, the 0.2901, times the probability that it's R-rated, which is a marginal probability. Overall, the R-rated is 0.4555. And the probability that it's a comedy is a marginal probability, which was 0.2922. And I'm pretty sure if you check that, that is correct here. These are in fact equal. But the logic, it seems quite mysterious here, I think, but there is a certain logic to this, and that's that this top equation that shows the two conditional probabilities actually should be thought of as looking like this. Probability of R times probability of C given R over the probability of C. And the idea here is that the probability is R-rated. This is known as the conditional probability you're looking at here is known as a posterior probability. And the prior probability, before you knew any additional information about what kind of movie it was, if you want to know the probability something is R-rated, you would start with what is the probability of an R-rated movie? That's 0.4555, 45%, a little over 45% R-rated. So this is the prior probability. You start with that. But now you have additional information. You know it's a comedy. So how do you adjust this prior probability? Well, you adjust it by saying, out of the R-rated movies, how many of them are comedies? So what is the probability that it's a comedy given that it's R-rated? What fraction of the time are the comedies R-rated? So this is known as the likelihood. It's the additional information that's being used to adjust the prior probability to get the posterior probability. And there are plenty of examples of Bayes' rule, and it can lead to some surprising results. But I'm just showing you here where we can get it from data. The Bayes' rule can actually just be derived from looking at the relative frequency with which these two things, these two conditional probabilities happen. And the two conditional probabilities, even though they both have C and R in it, they appear on the opposite sides of the equation, they are related through the use of two marginal probabilities. Like I said, probability theory can be quite subtle and quite complex. But the primary way that we will use probability theory is not looking at it like that at all. It's looking at, in fact, continuous values. So if we look at something like adjusted for inflation, this is the gross box office revenues. If you look at this distribution, it's a very skewed distribution. Most movies don't earn very much at the box office. Some of them are blockbusters. The highest here was $3.5 billion of box office revenues. That's adjusted for inflation. A lot of outliers with really high box office revenues, but most of them, again, are fairly low. The average movie, $80 million of box office revenues. The standard deviation is much larger than that. It's over 144 million. So what we could do is we could create a new column here. Let's call it standardized box office revenues. And to calculate this, we could use a formula. And for this formula, I'm going to look at the actual gross box office revenues. And I'm going to divide it by the standard deviation. Column standard deviation of box office revenues. Let's look at that column I just created, standardized box office revenues. Didn't quite work right. I think it has to do with some missing data in some of these rows. So, hold on a second here. Let me just see if I can. I think probably a better way to do this think it's one of, yeah, column standardize, a built-in formula, so let's just standardize. Well, it's still not exactly the same. I think it's because of the some missing data. And the mean, you notice, is very small. It should, in theory, the mean should be 0, and the standard deviation should be 1. It's not quite right here. It's off by a little bit. And it may also be because this distribution is so skewed. So the distribution that I actually want to show you, I would rather create a fresh one. Let's put into this column some random numbers. And this is from a normal distribution. Let's say you have an average of 100 and a standard deviation of 10. We'll see what that looks like here in a minute. Let me add some rows, like 10,000 of them. This is the most common kind of distribution you're going to see, which is called a normal distribution. It has this classic bell-shaped curve. It's symmetric, looks pretty much the same on both sides of the mean. The mean, I asked the computer to give me a mean of 100. You'll notice it's slightly different than 100, but that's because I only have 10,000 rows. So depending on the random numbers it chose, it'll be off by a little, but it's pretty close to a mean of 100 and a standard deviation of about 10, just slightly off because of the random numbers that are selected. If you create a new column called standardized, and for the standardized values, actually what you do, I think I used the wrong formula before. If you say how far from the mean are each of these values measured in standard deviations. So it's a built-in formula, but essentially we'll look at what the numbers look like. If you standardize column 1. So the first one was 101.45. The mean is about 100. So it's about 1.5 above 100. The standard deviation is about 10. So it's about 0.145 standard deviations above the mean. The second number was an 89.25. Yeah, it's almost 11 below the mean. But the standard deviation is 10, so it's really more like 1.1 below the mean, minus 1.07. So it's just remeasuring. It's like going from centigrade to Fahrenheit. Instead of using a scale of the original numbers, it's measuring in standard deviations how many standard deviations from the mean each of these numbers is. And if you look at this distribution, the mean, this is times 10 to the minus 14th. The mean is essentially 0 and the standard deviation is 1. So once you've standardized the values, measuring how far from the mean in standard deviations each of the data points is, you are finding a new scaled variable that on average will be 0 because on average the distance from the mean is 0, since the mean is the average. And the standard deviation is sort of measuring how far on average points are from the mean. The standard deviation of the standardized values comes out to 1. On average, each point is 1 standard deviation on average from the mean. So standardized values take any bell-shaped curve and convert them to measuring standard deviations from the mean. And you've all faced this at times in your life. Well, I'm sure you've all taken standardized test scores. So if you take the ACT test or the SAT or any of the assessment exams in schools, they are almost always scaled on to fit a normal distribution. And the numbers are reported to you, the results, in terms of your percentile rank. So it'll say, you know, you're at the 80th percentile of this test score. But the way they calculate that 80th percentile is basically because it's a normal distribution. The number of standard deviations from the mean will determine what percentile you're in. And there is a simple table for the normal distribution. All normal distributions can be reduced to what's called a standard normal distribution. That's what you're looking at here, where the mean is 0 and the standard deviation is 1. And in a standard normal normal distribution of any type, which since they can all be changed to a standard normal distribution, a rule of thumb, and this one you should try to remember because you will run across it time and time again. In a bell-shaped curve, almost everything happens within 3 standard deviations of the mean. It's like 99.7% of the time you'll be within 3 standard deviations of the mean. If you're ever more than 3 standard deviations from the mean, you are truly an unusual outcome. You may have heard about stock market Six Sigma events. That's when the stock market moves by 6 standard deviations in a day. Very rarely happens. It does happen actually. It happens more often than it should. It's not a normal distribution, the returns in the stock market. You may have also heard the term Six Sigma for quality control. Six Sigma is the idea that you want error rates to be reduced to errors to occur so unoften that they occur with a frequency of like analogous to 6 standard deviations away from what's typical. So Six Sigma is basically the idea of a high level of quality because it's a very rare time that you would ever be that far out of compliance. Everything happens within pretty much 3 standard deviations of the mean, as you can see from this picture. 95% of the time you'll be within 2 standard deviations of the mean. Notice here that 97.5% and the 2.5% go from about -2 to right around +2. 2 standard deviations take you 95% of this distribution. 1 standard deviation will take you about 2/3 of the distribution. So about 67% of the time you're within 1 standard deviation. If you get a standardized test score and it says you're 1 standard deviation above the mean, 67% of the time you'd be there. It's a symmetric distribution, so about a half of 33%, about 17% of the people scored higher than you. You'd be in about the 83rd percentile if you were 1 standard deviation above the mean. If you're 2 standard deviations above the mean, you'd be in the 97th, 98th percentile. That's a really good score. If you're 3 standard deviations above the mean, you may very well be the highest score on that test. And just to compare these 2 distributions, because they really are the same thing, just rescaled. Notice their shapes look exactly the same. If you don't have to turn your head. They look exactly the same, except the mean of this is 100 and the standard deviation is about 10. The mean of this is about 0. The standard deviation is 1. And they are, in fact, matched up perfectly. If you want to know the probability of being in this bar, it's the same as being in that bar. Or another way of looking at that is, if you look at the relationship between the standardized value and the original values, it's a perfect straight line. All it is a different measurement scheme. But the normal distribution underlies a lot of statistical theory, and so a lot of the probabilities we'll refer to have to do with knowing that something has a normal distribution and being able to say, well, if it has a normal distribution and if we know how many standard deviations we are away from the mean, we can say something about how likely it is for that to happen. So probability as its own subject, it's worth studying on its own, but its relevance to statistics is mainly that it is the language of statistics. So the basic idea of probability is important to understand. The mechanics, there's no way that you will get that without spending a lot of time studying probability. Mechanics don't come that easily. And I will never ask you to try to remember or memorize any formulas. If you have something where you have to calculate a probability, look it up. And in fact, there's absolutely no reason to not use resources to try to answer a probability problem. But in this course, you won't be dealing with having to calculate many probabilities. They're going to be calculated for you. You just need to understand when you're looking at a probability, what is it telling you? What does that number mean when it says there's a 20% chance of something happening? So this is an introduction to probability theory, and we will apply it in subsequent classes.